Good morning, everyone. Good morning. Hope all is well and everyone's all right. Hope you had a great weekend. Oh, wrong button. All right, so I said something in the chat. Yep. Good morning. Good morning. All right. So, looking to go ahead and get started. I know last class we did 5-1, so we're looking to get into 5-2. Anybody have any general questions before we get rolling? Is everybody good? All right. So let's look at getting into the notes. Let's go here. Hold on, looking for a certain word. What's my word? What's my word? Let's do it like this. Give me 1 second. This book's not giving me exactly what I want, so I'll do it like this. It will flow like that. Yeah, let's do it that way. And I think we did that up here. Yeah. All right, so when we look at starting to talk about how we would find our probability, first thing we know that we have is an experiment, which is any process with uncertain results that can be repeated. So an example of that is flipping a coin. Your sample space is going to be all possible outcomes of that experiment. In this case, that'll just be heads and tails. All right, then you got your event, any collection of outcomes in the sample space. All right, then they go into complement. Let me do it like this. All right, so then they introduce the complement, which would be all outcomes, all possible outcomes in the sample space that are not the event. So if our event was landing tails, then our complement will be heads. You know, all the events, all the outcomes in the event, all the outcomes in the sample space, if I can get it out right, all the outcomes in the sample space um, that are not the event. So we're talking about notation. All right, so as far as notation is concerned, if your event is labeled E, then the complement of the event would be E with this C superscript C. Same thing as if your event is A, then the complement of that event will be A with that superscript C. All right, any questions so far? All right, so getting into the summary of probability rules. I think they start off giving you three. Probability is always in between 0 and 1 inclusive. That 0 and 1 represents 0% to 100%. How do I write this? All right, so the probability of your complement is always going to be 1 minus the probability of the event, and vice versa. And then also, if you were to add them together, they should equal to 1. So the relationship of the probability of your event and the probability of its complement will always be centered and related to 1. Once again, if I have the probability of my complement, I can subtract that from 1 and find the probability of my event. If I have the probability of my event, I can subtract that from 1 and find the probability of my complement. And then also, if I were to add the probability of my event and the probability of my complement, it's supposed to add up to 1. So all of those are the same relationship, just, used in different ways. Right, like, well, All right, so the way we'll calculate the probability of A is that we will find a number of outcomes in event A and place it over the number of outcomes in your sample space. And just a quick example on how we'll do that. Let's say okay, so just a quick example of what we mean by that, and then we'll go to some legitimate examples. Going back to flipping our coin, we want to know the probability of landing tails. First thing is always best to establish your sample space and look at how many outcomes do you have in your, what are your outcomes and how many outcomes do you have in your sample space. So we already mentioned that your sample space for flipping your coin would be heads and tails. There are all of your possible outcomes when it comes to flipping the coin, heads and tails. So the number, and this is the short way of writing that. Let's say we use S for sample space. So in parentheses, the number of outcomes in our sample space is just 2, because all we have is 2 outcomes right here. All right, then our event. Let's call our event what we want. Let's call it. Let's just say. There we go. So our event is tails. I'll just call the event E for right now. And so number of outcomes in our event is just 1. So there's only 1 outcome, tails. So now we're looking at the probability of that event E. So you take the number of outcomes in your event, which is 1, place it over the number of outcomes in your sample space, which is 2. And that's how you calculate probability. So that's the foundation of what we'll be doing. All right, and of course we'll add more to it as we go along. Let's look at this first example. All right, so we have 10 dice in a bowl. Reach into a bowl that contains 5 red dice, three green dice, and 2 white dice. What is the probability of picking a red die, a green die, or a white die? All right, so first one, looking at picking a red die. First thing we want to do is establish our sample space. So the number of possible outcomes, we have 5 red die, 3 green, and 2 white. So that's 10. And if you just need to write it out, 5 plus 3 plus 2 is 10. We have 10 possible outcomes. So that's going to be our bottom number of our sample space. And then we're looking at the number of our event. We're talking about choosing a red die, so I'll call that event R. There are 5 red dice. That's where that came from. So the probability of getting a red die is a 5 out of 10 chance. And they would expect you to reduce that to the simplest fraction possible. So got a 50% chance of getting a red die. All right, any problems with that? All right, so we'll do the same thing for green. Sample space doesn't change. Still dealing with the same problem, so our bottom number is still going to be 10. This time we're looking at the number of green die, and that was 3. Probability of getting a green die would be 3 out of 10. Any problems? And just like before, that's the number. Got three green dice. So that's where we got that 3 from. The last one, a white die. Once again, the sample space is still 10. Number of white die is 2. So the probability of getting a white die is going to be 2 out of 10. That can reduce to 1 over 5. All right, any questions on those before we go to another example? So we're going to roll 2 dice and add the outcomes. What is the probability that the sum of the 2 dice is 7? All right. So once again, first thing we want to do is establish our sample space. All right. So what we have going on here is that we have 2 dice, die 1, die 2. And we have to explore all of the possibilities, all the combinations that can be created from these 2 dice. So in other words, when die 1 is 1, when die 2 is 1, die 1 is 1, die 2 is 2, 1, 3, 1, 4, and so on. So now instead of actually trying to write out all those combinations, remember we don't need to know every single combination, but we do need to know the number of possible combinations. The way we can calculate this is by recognizing that I have 6 faces on die 1 and 6 faces on die 2. And I didn't mention this before, but let me go ahead and do it just in case when you talk about die, because they came in with assuming that everybody has played, Monopoly, board game, whatever the case may be. And so I came in with that same assumption, but I shouldn't have done that. So when you're talking about the die, you have 6 faces. And you have these pips, to represent, what each face represents. So you have 1, 2, 3, 4, 5, 6. So we're talking about what's on the face of a die. Most of them, you have 1 through 6. And so you have 6 options or 6 faces on each one of your die. So if that's the case, if you want to know all of your possible combinations, the total number of possible combinations, you can just multiply those together. And that'll give you 36. So now if you had a die that had 8 faces, then let's say you had one that had 6 and the other one had 8, then it'd be 6 times 8. So that 6 just represents the number of faces on the die. And so now this 36 is going to represent the number of possible outcomes, from the 2 die. When you roll the 2 die to 36, it's going to represent the number of possible outcomes that can be created. All right. Any questions on that? So that's going to be our bottom number. That 36 will be our bottom number. Let's go. All right, so let's look at our event. Our event is to roll a 7. So it means when you roll your 2 die, no, you roll your 2 dice. When whatever faces they land up, they need to add up to give you 7. So you want to explore how many possible ways that can occur. And you want to be systematic in how you do it. So you would just start off with 1. And then, so if die 1 is 1, that means die 2 would have to be 6 in order for them to add up to give you 7. If die 1 is 2, that means die 2 would have to be 5. If die 1 is 3, that means die 2 would have to be 4. They're adding up to give you 7. But also, die 1 being 4 and die 2 being 3 is a different combination. So then you have to do 5 and 2, and then 6 and 1. So the number of your possible outcomes that can create a roll of 7 would be 6 different ways that could occur. All right, any problem with that? So that's going to be our top number. So now the probability of that event is going to be 6 over 36. And that can reduce down to 1 over 6. So you got a 1 out of 6 chance of rolling a 7. All right, any problems? All right, and at the next thing, I think we'll use the same, yeah. Let's look at this chart. All right, so we're going to use this chart for this example and the next example. We got 17, 68, 27, 12, 72, 40, 98, 4, 0, 8, 10, 59, 15, 84, 28, 33, 61, and 125, 397, 143, and 665. All right. And so in the purple, education and marital status for 665 randomly selected U.S. residents. All right. So the first question pertaining to the chart. Suppose we select at random from the collection of 665 people. What is the probability that the person is married? All right. So as always, we want to establish our sample space. That's our total number of possible outcomes, total possible number of outcomes. So that's going to be 665. That's our total number of people. Say it right here as well. All right. So what's the probability that the person that's chosen is married? So then we're going to look at the married category and look at the total number of people married. That would be 408. All right. So the probability of picking somebody married is going to be 408 over 665. And my math lab will let you know how, what form they want the answer in. They want it in decimal. It was 0.614. Or if they want it in percentage, that'd be 61.4%. You move your decimal two places to the right. Yep. So either one, it just depends on, like I said, what Math Lab asks of you. If they ask for the decimal or percentage, just always make sure you're paying attention to, how many decimal places they ask out, what you round it up to. All right, problems with that one before we look at the next one. So what is the probability that the person has a college education or higher? All right, so our sample space has not changed, still 665, still dealing with the same problem. So now we want to look at the number of people who have a college education or higher. So that'd be 143. You're talking about going this way. Marriage was, this column. That was the first problem, but college education or higher is this row. So we're looking at 143 total number. So that's 143 over 665. All right, so C says what is the probability the person is married and has a college education or higher? So now we're looking at married and M and C, married and has a college education or higher. So we go back to our chart. And so married is right here. College education is right here. So they meet up at 98. So those are the number of people in this 665 that's married and have a college education. All right. So that'd be 98. So the probability of them both would be 98 over 665. Any questions? All right. Um, all right. So they just dropped, a statement on what and would do for you, because that was introduced in C. It says the word and consists of only those outcomes that are both events. So that's why, we only use those 98. The reason why they emphasize and, because in the next example, they're going to use or, which would be a little different for us as well. All right, anybody holding on to the purple? All right, so the word or consists of all outcomes that are only in A, that are only in B, or that are in both. So everything that involves A and B is the word or. Now remember, and only used those who are A and B. But, let's say if we were looking at, I know we didn't mention Venn diagrams, but let's just say if we decided to use a Venn diagram to explain the difference. Now, let's see. So if I let circle A represent my event A and circle B represent my event B, the red shade would represent both of them. That's what they have in common. The red shade just represents what's in common with both. Now, as far as or is concerned, or is going to be, let me do it like this. So or will represent the green, the red, and the purple. So or is giving you a choice. You can either just be A, you can just be B, or you can be both of them. So that's what or is. Wherein, as I mentioned, going back to and is only going to be the red shade. What do they have in common? That's and or is all of it. All right. Any questions on the differences between and or? Making sure we're all right. All right. So now if we go back to the question, what is the probability that a person is single or married? So we know our sample space still should be 665. We haven't changed the problem, still dealing with the same chart. So now we need to look at being single or married. Also take note, it's impossible to be single and married at the same time, right? Can't be both. You're not dealing with any complicated situations here or any entanglements, right? It's just being either you're single or you're married. So as far as this chart is concerned. All right, so is everybody done copying this? Can I scroll up a little? All right, I'll come back down. Just want to go back to the chart. So when we go back to our chart, when you talk about being single, total number of single people is 112. Total number of married people is 408. So we would just add those together. Let me write it like this. Well, we use S for the sample space, looking at being single or married. I'll just let our event just be that way. So we're looking at 112 plus 408, which would be 520. So the probability of that occurring would be 520 over 665. 78.2%. All right, any problems with that one before we look at another one? All right. Married or lost my spot or has a college degree.
All right, so what is the probability the person is married or has a college degree? All right, once again, bottom number 665. All right, so okay, before I scroll back up to the chart. All right, so now here we have to be careful. It's a little different than the last problem. Same thought process, but like I said, we have to be careful. Now, remember I mentioned it's impossible to be single and married at the same time, as far as our chart is concerned, right? So there was nothing that was in common when we looked at our values. If I go down this row, single people over here, married people over here. But now we're talking about being married and then having college. Notice if we were to just use the 143 and the 408, that would be the easy route. But you have to recognize that 98 is being counted twice. You know, those people who are married and have college or higher degrees are being counted twice. So you can handle this one of two ways. Either you can, add all these together, and then when you add this one, you skip the 98. Oh, you don't want to add that 408, sorry. Where you do 72, 40, 98, then 27, 15, 3. You just got to make sure you don't use 98 twice. Or you can add this, and then subtract a 98. So I'll show you what I mean, but just saying that we have two options here of taking care of these. So let me see, I got 70. So let me do it like this. Let me see. Got 70, 240, 98, 27, 15, 3. Um, 408. All right. So either way, you'll get your 453. You can add up each individual piece, or you can add the two totals and then subtract what they had in common, which was that 98. Like I said, you don't want to count the 98 twice. All right. Any problem before we finish it off? So the probability is going to be at 453 over 665 and 68.1%. All right, got one more thing in this section that they emphasize, and then we'll be good to go. So we actually have a formula for this right here that we'll get to as far as rule 4 is concerned, but we'll see it play out in a second. Everybody good? Can I scroll up? All right. So mutually exclusive events is the next thing this section goes to. So the events that do not have any outcomes in common, or basically it's impossible for these events to happen at the same time. So that goes back to you know being single and married. Let me write it like this. So events of being single and being married are mutually exclusive. I'll just bring it over some. All right, so rule 4, probability of A or B occurring. And this was that last thing that we did in that example. You take the probability of A, add it to the probability of B, and then you subtract what they have in common. All right. Now for mutually exclusive events, which is what we're doing right here, all you have to do is add your probabilities together because they don't have anything in common. And so that's why you don't have this piece when you have mutually exclusive events. So that goes back to what we did with single and the married probabilities. All we did was add those two together, and we didn't have anything that they had in common. All right. Any questions on that before we do another example? All right. So first example, with this new information, roll a fair six-sided die. Find a probability that a die shows an even number or a number greater than 4. See, number greater than 4, even number greater than 4. I want to do a number greater than 3. I think I like 3 better. I want to do 3. Yeah, let's do 3. All right, so we have 2 events here. We have an even number greater than 3. So I'm going to call E even number. And we'll call G greater than 3. So our sample space, yeah. Sample space is 6. You have 6 faces to our die. Now when I look at even number, that's 2, 4, and 6. So the number of even numbers is 3. We have 3 numbers that fit that description. So the probability of getting an even number is going to be 3 over 6. All right. Any problems? Everybody good? So greater than 3. Number of our sample space is still 6. Talking about greater than 3, we have 4. You know what? I meant to do greater than 2. That's what I want to do. 4, 5, 6. But it's all good. Don't leave it. Anyway, it's 4, 5, 6. And the number of numbers that are greater than 3 is 3. Probability is 3 over 6. Any problems? Any problems so far? I think I want to change that next time. All right. So now, we always have to ask ourselves, are the events mutually exclusive? Because remember, that's going to dictate, how we look at, calculating our probability. Whoa, what happened there? So it's going to dictate how we look at calculating our probability. So are the events mutually exclusive? The answer is no. They have 4 and 6 in common. All right, is everybody okay with that? So these events are not mutually exclusive because they have 4 and 6 in common. So we don't want to, excuse me, we don't want to add these probabilities together, because just adding them together, that's not going to be a legit answer because it's counting 4 and 6 twice. Because this 3 over 6, okay, yep, get my number back. Okay, there we go. So this 3 over 6 has 4 and 6 in it. This 3 over 6 has 4 and 6 in it. So just adding them together would actually give us a 100% chance of getting an even number or greater than 3, which is not accurate. So that means we need to find a probability of even and greater than 3. Sample space is 6. Number of numbers that's even and greater than 3. 4 and 6. Probably should have, yeah, I stuck to that. My erasers and stuff not working. There we go. Come on, guy. All right, let me write this over here. For some reason my pen isn't working well. Here we go. Sorry, trying to stay consistent with how we set up these notes. All right, so then we have the probability of E and G. It's going to be 2/6. All right, so before we finish this off, any problems with what we've done? All right, so this is what we're looking at as far as the formula is concerned. The probability of your an even number plus the probability of a number greater than 3 minus the probability of both of them. So it's 3/6 plus 3/6 minus 2/6. That'll be 4/6. And once again, you are expected to reduce if possible. So you got a 2 out of 3 chance of doing so. All right. Questions on what we did? So we got one more
I have
that leads into it. Yep, I'm listening.
we were going over rule 4 and it was like PA plus PB subtract what's in common. Could you go over one more time? I'm sorry. What would be subtracted that's in common? Would it be like okay. It would be that.
Yeah, because they have 4 and 6 that are
Okay.
in common with each. And so the reason why we do subtract is because we don't want to count them twice.
Okay. That's right. I understand. Okay. Thank you.
Yep, not a problem. So we have one more example still piggybacking off of this information. So everybody good before we go to the next one? Just want to make sure. Almost finished, y'all. Almost finished. I think I was doing dark blue. Yep. So I want to stay consistent. Come on. All right. So this last one, we find the probability. All right, so found a probability that the, should have said die, right? Yep, left out die. That the die shows an even number or the number 5 on top. All right. So let's look at our events individually again. So even number, even though we've already explored that one, we just go through the motions, make sure we're good. So once again, establishing your sample space, that's going to be 6 for us. And erase. Really? Okay. All right, there we go. So even number once again is 2, 4, 6. The number of even numbers is 3. Probability of getting an even number is 3 over 6. Now the next one, talking about rolling a 5. Sample space is still 6. This time, I guess we can call it F. There's only one 5. So the number of outcomes in this event is just 1. So the probability of getting a 5 is 1 out of 6. So before we go any further, make sure we're okay. All right, so now we got to go back to our question. Are these events mutually exclusive? In other words, do they have anything in common? Oh, let me do that. So are these events, why is my eraser not working? Okay. So are these events mutually exclusive? The answer is yes. They are mutually exclusive. No outcomes in common. You know, if we go back to the last one we had, you said, are they mutually exclusive? The answer was no, because they have 4 and 6 in common. These are mutually exclusive because they do not have anything in common. So since they are mutually exclusive, this means that we can just add the probabilities together because they don't have anything in common. Remember that other piece, the subtraction part, was because there was something in common. So 3 6 plus 1 6 would be 4 6, which will reduce down to 2/3. All right. Any questions? Any questions? All right. So try the stuff out. 5.2 has already been posted. Um, let me know if you have any questions, and then we'll go from there. Next class, we'll get into 5.3. Um, Not sure if we'll be able to touch 5.4, but I know we'll do 5.3 and then go on from there. All right. Any questions or concerns before we close out? Is everybody good? All right. Well, you guys have a good one. Be safe, and I will see you on next class.
Have a good day.
All right. Thanks. You do the same. Is gone.